In section 5, we've got two main theorems that we want to get used to seeing, and they basically come from these two pictures. One of them is coming from where we have a triangle, where we have a parallel side drawn inside of the triangle. Notice this is not a mid-segment like we had earlier where it was drawn from the middle. It can be drawn anywhere on here. The other one is drawn from angle bisectors. So when we see that those two angles are the same, that's where the other relationship comes in. So looking first at 7.4, this book calls it the Sidesplitter Theorem because we're splitting a side in half. Then what we look at is when we have parallel lines, the triangle is going to be divided into proportional parts, or at least the side of the triangle. So we can match this up by thinking the parts on one side, maybe A over C, would be equal to B over D. We could also think about it as a part on this side, so like A, with its matching part on the other side, B, C over D. So notice the orientation of this could be however it needs to be. It could be the parallel sides are on the bottom, or we could turn it on its side like that, just as long as we have those parallel sides and the parts. We can also think about this as being drawn anywhere on the side. That relationship is still going to be true, the A over C, B over D, however small or big that inner triangle is. So we would use it in a problem like this. We notice that we have the parallel sides there, so we're going to match up corresponding parts. I might start with the x plus 1 here, just start with x, and I can match that with either going across to x or match the same sides. I'm going to go across, I think, this time. So over to x, and that would be equal to the 12 over the 9. We cross multiply, make sure to distribute that 9 to everything, equal to 12x. That gives us 9 equals 3x. Or dividing, we get x equals 3. Now be careful, if they give us the long side as our part, it doesn't really fit this theorem. Now notice what we do have here though, is that we have, if I pull this out, I do have similar triangles. We still have these angles here because of the parallel lines. We have, well, first of all, the reflexive property there, but because of the parallel lines we would have these two angles the same, as well as these two angles. So these two triangles are still going to be similar because of those parallel lines. What we have to be careful about if they give it to us this way is that this side is not 18, it's actually 18 plus 6, which gives us a 24. So if I'm going to set up this proportion and look for x, I would start with x, it corresponds to 16 in the larger, and the 6 is in the smaller triangle with x corresponds to 24. So we need to pay attention to that when that triangle is drawn on the inside there. There is a corollary to this theorem, and this is even if I don't complete the triangle, notice I could extend this and keep going up, it would eventually become a triangle. But rather than doing that, I'm just looking at multiple parts inside of here. So we could put the x over y equal to m over n. So x over y, m over n. But I could also, notice, extend this. Let's say I get another pair of parallel lines down here. And let's say we've got Z and maybe O. So if I wanted to look at another proportion here, so x over y, well, so let's go with some parts on the other side. Maybe I went with x over m would be equal to y over n, but it would also be equal to the Z over O. In this next part of 7.5, they call this the triangle angle bisector theorem, which pretty much says what we need. We've got a triangle, and within the triangle is this angle bisector. So we could think of this as being extended if we needed to, but usually this is just drawn within the triangle. The important thing with this is that these are marked as congruent angles. If they are, then we have this relationship. If I take A over C, it will be equal to B, so the other, and that matches with D. Using this in a problem, notice this one's spun around, it's the opposite direction of the other one, but we still have an angle bisector here because these are marked as congruent angles. So if I start with, say, x, its matching side would be the 18. Since I had the x, which is on the bottom there, I'm going to take this 12 here, which will go over to 10. This is going to give me 10x equals 216. Divide both sides by 10, which gives us 21.6.